Okay guys, this is a problem that I didn't get to in the last video dealing with the gas mixing problems, and I just wanted to point out that this one here is a little bit different. The reason it's different is that the gases, so we're mixing 3 moles of H2 and 1 mole of N2, and they start off in equally sized compartments, then they mix together. The reason that those formulas don't quite work, that is the formulas that we derived here, the reason these formulas don't quite work is that the pressures are the same, or they're not the same for the two individual gases, and so it's not quite the same formula. Nevertheless, you still can do this problem. You just have to go back to more or less the beginning. So you want to calculate the delta S of mixing. You would need to do the expansion. I guess this would be hydrogen. So this will be the final volume over the initial volume, which I'll just call V, and then do the same thing for the nitrogen. In both cases, the two initial volumes are the same. We'll just call them V, and the two final volumes are the same. In fact, they're twice the original volume. And so you cancel out, and you get this. You'd be NH2 plus N2 R natural log of 2. Really, this is an extensive formula. I need to divide by the total number of moles to give me the intensive version. And it would be that for this particular problem. And then the delta G of mixing would be minus T times that delta S of mixing, so minus RT natural log of 2 to give you the delta G for this problem. I'm going to switch gears again, and we're going to start talking about ideal solutions, generally speaking, liquid solutions. So we'll be talking about mixtures of volatile liquids. Volatile liquids have low boiling points, so it's easy to boil them. And as a consequence of having low boiling points, they also have high vapor pressures. Remember this diagram. I always like to remind people what vapor pressure is before I start talking about it a whole bunch. You've got some liquid in a sealed container. Okay? It comes into equilibrium with the vapor phase, the partial pressure that develops when the liquid and gas are in equilibrium. That's called the vapor pressure. And then we learned in the phase diagram chapter that as you increase the temperature of the liquid, the vapor pressure increases. Once the vapor pressure equals the atmospheric pressure, then the liquid starts to boil. So if you have a low boiling point, that means you already have a high vapor pressure. And so that's what makes up a volatile liquid. Low boiling points and high vapor pressures. The interface between the liquid and the vapor molecules are constantly going back and forth. And if you've got enough liquid in the container and a small enough volume, then you can the two can come to equilibrium, and that's what gives us the vapor pressure. And so this what this diagram does is it illustrates the case for when you have two components. So now we're considering a solution, A and B, components in both the liquid phase and in the vapor phase. And what we need to keep in mind as far as once this system comes into equilibrium, the chemical potential of component A in the liquid phase will equal the chemical potential of component A in the vapor phase at that given pressure, that vapor pressure. The same thing is also true for component B. So we could write that the chemical potential of component B in the liquid phase equals the chemical potential of component B in the gaseous phase at its vapor pressure. However, you would not cross, like so for example, you would not say that the chemical potential of component A in the liquid phase equals the chemical potential of component B in the vapor phase. That's not true. Likewise, you wouldn't say that the two chemical potentials of these substances are the same either. So it's really just for that same substance, in all phases when the system is in equilibrium, the chemical potentials are the same. And so that's what we're illustrating here with this equation. So what we're doing in this first equation is we're considering the chemical potential of a pure liquid. And in my notes, we'll be using the star, the superscript star, to denote a pure liquid. So this is the chemical potential of substance J in its liquid state as a pure component. It's equal to the chemical potential of that component in the vapor phase as a gas with that particular vapor pressure. Okay, so this is nothing more than just phase equilibrium. The chemical potential in one phase equals the chemical potential in the other phase at this particular pressure. Now on the right-hand side, what we're doing is we're taking an equation that we've derived previously, okay, relating the chemical potentials. So the chemical potential of a gas at a particular pressure is referenced against the standard state chemical potential plus this correction factor involving the ratio of the pressures. Now when we form a solution, okay, we drop the star notation. And so here we've got the chemical potential of component J as a liquid in the solution is equal to the chemical potential of component J in the vapor phase with its particular partial pressure. But the thing to keep in mind is that the vapor pressure of that component in the solution is not the same thing, it's not the same value as the vapor pressure of the pure liquid. So these two pressures are different from one another. And so what we reference against in the case of a solution, we reference the chemical potential of the component J in the solution. We reference it relative to the pure liquid's chemical potential. Up here, we referenced it relative to the standard state of the gas. Here, it's relative to the pure liquid. And then the correction factor involves a ratio of vapor pressures. So this is the vapor pressure of component J in solution. This is the vapor pressure of component J when it's a pure solvent. We'll introduce the idea of an ideal solution. An ideal solution is one where all of the components of the solution have roughly the same size, roughly the same shape, and the same intermolecular interactions, and they obey Raoult's law. So that's the definition of the ideal solution. Raoult's law, it's an empirical law where Raoult noticed that for certain solutions, the vapor pressure of the components in solution were proportional to the mole fraction of that component in the liquid phase. Okay, so again, this is the vapor pressure of the component in solution, okay, in the vapor phase above the solution, I should say. It's equal to the vapor pressure of the pure component weighted by the mole fraction of that component in the liquid phase, right? The mole fraction varies between 0 and 1. For a pure liquid, it's 1. So of course the vapor pressures, for a pure liquid would equal the vapor pressure for a pure liquid. When the solution is when that component is very dilute, this number goes down to 0. The vapor pressure of that component goes to 0. And so taking this relationship here, which is very general, in fact, the only assumptions that go into this are that the vapor phase obeys, that the vapor components are ideal gases. Substituting in Raoult's law for this ratio of pressures gives us this relationship here. And what I want to point out, since mole fractions are always less than 1, the natural log is always negative. What this tells us is that the chemical potential of a component in an ideal solution is always less than the chemical potential of the pure liquid. In essence, what it tells us is that solutions always form spontaneously. At the very least, ideal solutions always form spontaneously. And the effect here is due to entropy. The reason it's due to entropy is because all components have the same size, shape, and intermolecular interactions. There's really not a large change in energy when you mix an ideal solution together. Now, I'm not saying that the components don't interact with one another at all. The ideal solution is distinct from the ideal gas in that sense. In the ideal gas, the components don't interact with each other at all. In the ideal solution, they do interact. It's just the components interact with each other the same as they interact with themselves. And so there's still no energy change. So here we have a Raoult's law type of problem. We've got, we're given the vapor pressure of pure benzene at 20 degrees Celsius and the vapor pressure of pure methylbenzene at the same temperature as 25 torrs. Then we're being asked to calculate the vapor pressure for each component in an equal molar mixture. So methylbenzene is also called toluene, and so I'm just going to say that the vapor pressure of benzene is 75 torrs. The vapor pressure of toluene is 25 torrs. We're considering an equal molar fraction, which means that the mole fraction of benzene equals the mole fraction of toluene equals 0.5 in this case. So to calculate the vapor pressure of each component in solution, that is when you make the solution, what's the vapor pressure of each component above the solution? The vapor pressure of benzene would be the mole fraction of benzene times the vapor pressure of benzene when it's a pure component. Same thing for toluene. Both components obey Raoult's law. And so we're going to have 75 torrs times 0.5 and 25 torrs times 0.5. And that's going to give us our answers here. So 37.5 torr, 12.5 torr. What would be the total vapor pressure of the solution? The total is PB plus P total, or sorry, PB plus PT. So 50 torrs. Calculate the mole fractions of each component in the vapor phase. Well, the definition of mole fraction for gases, or one of the definitions, I should say, for benzene, you would take the partial pressure of benzene and divide it by the total. For toluene, you do the same thing. And so we'll get those numbers real quick. .75, 0.25. So we started off in the liquid phase with an equal molar mixture of benzene and toluene. And then when we look at the composition in the vapor phase, we see that the vapor phase is enriched in benzene and depleted in toluene. That's a general truism. The vapor phase above a solution is always enriched in the more volatile component. Benzene has a higher vapor pressure than toluene, and so it's no surprise that we find a higher concentration of benzene in the vapor phase in the solution. Here's a diagram illustrating this problem. Here we've looked at a particular concentration. This diagram shows the partial pressures as a function of the mole fraction of the component in solution. So I don't know, we could say mole fraction, let's see, this would be the mole fraction of toluene in our example here. Okay, so this line here, this would represent the mole fraction of toluene. I'm sorry, this is the mole fraction of toluene, and this line represents the partial pressure of toluene. When the mole fraction of toluene is 0, we have pure benzene, and so the partial pressure of toluene would have to be 0. Over here, when the mole fraction is 1, we have pure toluene, and so the vapor pressure for toluene would be that of pure toluene. Okay, and so this would be like 25 torrs. The red curve represents the partial pressure of benzene. Okay, and so when the mole fraction of toluene is 0, we have pure benzene. This would be the vapor pressure of pure benzene, and that's 75 torrs. Notice it's above the 25 torrs here for the toluene. As the concentration of benzene decreases as you go this way, the vapor pressure of benzene decreases and it goes to 0. The total vapor pressure of the solution is a sum of these two curves. And so on the one hand, it would be when it's pure benzene, the total pressure would be the vapor pressure of benzene. And then on the other end of the diagram, when it's pure toluene, the total vapor pressure of the solution would be that of pure toluene, and then everything in between. You can anticipate an exam problem just like this one, and then also you'll need to be able to draw the appropriate diagram for that problem. I guess this would be the example from our, it's exactly what I said, I believe. It's the same diagram, just here benzene and toluene, they just put the names on the figure. Most solutions do not obey Raoult's law. That is, most solutions are not ideal solutions. This is very different from gases, where most gases obey the ideal gas law. However, for solutions, very few solutions obey Raoult's law. And the reason for that is that molecules, when they're in the liquid phase, they interact with each other strongly, and molecules are usually not the same size and shape and have the same intermolecular interactions. So we get all sorts of deviations from Raoult's law. We can talk in terms of negative deviations and positive deviations. This graph is an example of a positive deviation from Raoult's law. So here we've got a solution of carbon disulfide and acetone. So this is the vapor pressure of acetone in solution. This is the vapor pressure of carbon disulfide in solution, and this is the total vapor pressure that's measured. Well, the Raoult's law, the ideal solution model, would predict straight lines, and then the total vapor pressure would be a straight line from this point down to that point. Because the measured vapor pressures are above what Raoult's law would pick, we call it a positive deviation. What a positive deviation suggests is that the carbon disulfide and the acetone have a greater tendency to vaporize when they're in the solution than when they are not in the solution. And so that indicates that the attractive interactions between carbon disulfide and acetone aren't quite as attractive as the interactions within pure carbon disulfide and the interactions within acetone. It's not that they're not attracted to each other, they are, because they form a solution, otherwise they'd be gases. It's just that the interactions are not as strong in the solution as they are in the pure components themselves. Let's see, I'm looking for a negative deviation from Raoult's law, and this would actually be a negative. This figure here illustrates a negative deviation from Raoult's law. We've got acetone and chloroform that are mixed together. Let me see if I can figure out what's going on here. So this would be mole fraction of chloroform. So this is the chloroform curve right here. This represents the vapor pressure of chloroform. This represents the vapor pressure of the acetone. The straight line that you see here and this straight line that you see here, that's what you would predict from Raoult's law. And the measured vapor pressures you see are smaller. They're lower than what you would expect from Raoult's law. And what that indicates is that the interactions between acetone and chloroform are such that they are more attractive than the interactions within acetone and the interactions within chloroform. That is, the two like one another, and so there's a smaller tendency for them to vaporize. Hence, the vapor pressures are depressed compared to the ideal result. We'll go back a little bit. So by analyzing or just by looking at the deviations from ideal behavior with respect to the vapor pressure curves, you can actually say something about the nature of the interactions between the solute and the solvent. We're going to introduce for these non-ideal cases, we're going to introduce another model called the ideal-dilute solution model, which is distinct from the ideal solution. Okay, so the ideal-dilute solution is different than the ideal solution. In the ideal-dilute solution model, in the dilute limit, that is when one of the components is present in a very small amount relative to the solvent, we find that the solvent obeys Raoult's law and that the solute obeys something else called Henry's law. Okay, so what's going on here with this notation? The vapor pressure of component J, in the limit that the mole fraction of J goes to 1, that is when the solution is almost pure component J, the vapor pressure obeys Raoult's law. However, in the opposite limit, when we're considering a solute, the vapor pressure of the solute, when its mole fraction is going to 0, obeys a linear law, but it's not Raoult's law, it's Henry's law. That is, the constant involved is not the vapor pressure of the pure component, it's some other constant called the Henry's law constant. And we can see evidence of that in this diagram right here. So here we've got the mole fraction of carbon disulfide. So on this side of the graph, right, when the mole fraction of carbon disulfide is close to 1, carbon disulfide is the solvent. And this dashed line here, this is Raoult's law. And we see that as the mole fraction goes closer and closer to 1, the carbon disulfide vapor pressure curve converges to the Raoult's law. At the other end of the diagram, where carbon disulfide would be the solute and has a very small concentration, we see that the vapor pressure curve for the carbon disulfide is linear. However, it does not have the same slope that you would get from the Raoult's law. It's a different slope, and that slope is the Henry's law constant. In this graph, acetone does the same thing. It's just the ends are reversed. Over here, acetone is the solvent, and so you see that the acetone vapor pressure curve converges to that Raoult's law line. whereas when the solution is almost pure carbon disulfide, the curve is linear right here at the edge. It's just that the slope is very, very steep and has nothing to do with the Raoult's law slope. It's obeying Henry's law. So the solutes are obeying Henry's law. The solvents are obeying Raoult's law. This is another example of that. It's basically the same thing that I said before. An explanation. In the ideal dilute limit, solvent molecules basically are interacting with other solvent molecules. Okay, and that's represented by these blue spheres here. However, the solute is in a completely different environment than it would be if it was pure solute, if that makes sense. So here the solute is in a completely foreign environment, and so it's behaving totally. It's not behaving like it would if it were in its own, if it were in a pure component. And so that's the distinction between the Raoult's law constant and the Henry's law constant. So here we're given some data. So we're looking at the chloroform and acetone. We've got mole fraction of chloroform over here. We've got the vapor pressures of chloroform and acetone. And so the next graph plots those. Here it is. So this is the chloroform curve. This is the acetone curve. You know, from this you can determine, from this data, you can determine the vapor pressures of the pure components, right? So this is the vapor pressure of acetone, that's the vapor pressure of chloroform. And then by looking at the slope of chloroform in this region right here, so by using these 2 points to calculate a slope, that's going to tell you the Henry's law constant for chloroform. By looking at these 2 points and taking the negative sign, that's going to give you the Henry's law constant for the acetone. Here we've got a little problem involving Henry's law, I believe. So we're being asked to estimate the molar solubility of oxygen in water and a partial pressure of 21 kilopascals. So the idea here is that you've got some water and then you've got O2 above it with some pressure, and that causes the O2 to become this should be aqueous. This is the gas phase. Some of the oxygen becomes aqueous, and we're being asked to calculate that using Henry's law. And so I'll go to the previous slide here. So essentially the solubility of O2 is going to be equal to the Henry's law constant here times the partial pressure of the O2 above the solution. Just check out the units real quick. The Henry's law constant is kilopascals. Let's see, I've got it backwards. The partial pressure is the Henry's law constant times the molality. In this case, I'm going to use the symbol B for that. Check out the units. It's kilopascals, kilograms per mole. For K, for B, it'll be moles per kilogram. Those cancel out, and you get the pressure kilopascals. So that's how we're using Henry's law in this problem. And so they want us to calculate the molar solubility. What we're going to get out of this is the molality. So if we solve for B, we'll take the 21 kilopascals for the partial pressure, and we'll divide that by divide that by K, which is 7.92 times 10 to the 4 kilopascals kilograms per mole. .65 times 10 to the minus 4 moles per kilogram. So that's the molality. They want us to convert this to probably molarity. And so what we'll do is we'll assume that we've got 1 kilogram of solution, which means that the number of moles that we have is going to be 2.65 times 10 to the minus 4. And what we need to do is divide by the volume of the solution. So we have, they say, assume that the solution has a density equal to that of pure water. We've got 1 kilogram. And so what we'll do to get the molarity, C, is to take the number of moles, 2.65 times 10 to the minus 4. We'll divide by 1 kilogram, and then we'll divide that by the density, divided by 0.997 kilograms. Let's see, am I doing that right? No, I don't think so. I think I got it all mixed around. The molarity will be the number of moles. We will take it'll be decimeters cubed over 0. I guess I did have it right. Kilograms times 1 kilogram. That'll be our molarity. .64. It's not a big difference here. That'll be moles per liter for the molar concentration. And the reason it's not that big a difference is that the density is so close to 1. Well, I'm going to go ahead and stop this video here, and we'll talk about more properties of solutions in the next one.